All right, good afternoon. Welcome. Welcome to those of you here in our live studio audience and to those of you watching via Zoom. I'm Marlon Bornett. I'm a professor and a member of the METRANS Executive Committee, and I am pleased to welcome our speaker today. Dan Wei will be talking to us about the economic impacts of cargo handling equipment electrification at the ports of Los Angeles and Long Beach. And Dan is a research associate professor here in the USC Price School and has been with us here in Price, I know, for as long as I've been at Price and maybe longer.
More than 10 years.
More than 10 years. And it's just been wonderful to have Dan with us. She is an expert in economic impact modeling. She's done substantial work around climate change and economic impacts more generally. And so we really look forward to hearing from her. Dan's research focuses on the economic consequences of natural and man-made hazards and economic modeling more generally. She holds a Bachelor of Engineering degree in engineering physics and a Master of Science degree in public policy from Tsinghua University in Beijing, and a PhD in geography from Penn State University. And so, Dan, welcome. And let me go ahead and put you into your slides into screen share for you. And yeah, do you want me to have this view or?
Yeah, I think that will, the previous one.
Okay,
Is better.
all right. Let me give you Dan Wei.
Thank you. Good afternoon, everyone. So I welcome you to come to today's METRANS seminar, both in person and virtual on Zoom. So today I'm very happy to have this opportunity to share with you one of the most recent studies that Professor Jan Giuliano and I completed recently. So in this study, we analyzed the economic impacts of cargo handling equipment electrification at Port of LA and Port of Long Beach. All right, sorry. Thank you. Okay, so first of all, I would like to just give you outline of today's presentation so that you will know what is going to expect. So first of all, I'm going to provide you a very brief background of the study. And then I will provide you some more details of the specific case study, that is the electrification of cargo handling equipment at the Twin Ports, San Pedro Bay Twin Ports. And after that, I'm going to talk more about how we quantify the direct changes in cost and savings for this whole electrification transition. And then I'm going to provide a general description of the macroeconomic impact analysis model, the REMI model that we used in analyzing the macroeconomic impacts of this policy. And after that, I'm also going to talk about how we link the direct economic impact analysis results in terms of the changes of cost and savings by the deployment of electric cargo handling equipment and the inputs of the REMI model. And after that, I'm going to show you the macroeconomic impacts of this case study for the base case. Because there are a lot of uncertainties in terms of some key parameters and assumptions that we made in our analysis. I'm also going to talk about some sensitivity analysis that we conducted so that we can, obtain more insights in terms of how the changes in those key assumptions would affect the bottom line results of our economic impact analysis. And finally, I'm going to conclude my presentation with a summary of key findings in this study. All right, so a little bit of,
Someone typed something in the chat.
okay. Oh yeah,
Okay.
if anyone have questions, feel free to type in chat. Yeah. Okay. So this study is part of the project that we want to track the economic competitiveness of the freight sector under the implementation of the California Sustainable Freight Transportation Freight Action Plan. Okay, so the California Sustainable Freight Action Plan went into effect in July 2016. So we all know that the freight transportation sector is very vital to both the state and the nation because its major contribution to the movement of goods and commodities and also smooth flows of trade domestically. However, at the same time, we know that freight transportation sector contribute a large share of emissions in California. And the state has established very ambitious goals to mitigate greenhouse gas emissions as well as other types of pollutants. And so the existing, so first of all, the California Sustainable Freight Action Plan, its primary goal is to integrate investment opportunities, regulations, policies, and programs in order to help the freight transportation sector to improve efficiency and also transition to near zero emission or zero emission fleet and technology, as well as to enhance the economic competitiveness of this sector. The current regulation by CARB, California Air Resources Board, on cargo handling equipment was first initiated in 2006. So the regulation, the existing regulation, aims to identify the best available emission control technologies that can be applied to all kinds of fossil fuel powered cargo handling equipment. And currently the COP staff, they are actually evaluating and making assessment on the availability and also the performance of zero emission cargo handling equipment that can be used as alternatives to all types of combustion powered cargo handling equipment. So it is expected that the new regulations and rules will take effect starting in 2026. Also at the same time, because the emissions from cargo handling equipment is one of the major emission sources at the port complex. So in the Port Clean Air Action Plan, transition to zero emission cargo handling equipment has been identified as one of the major strategies to help to reduce the emissions at the port complex and help to protect and enhance public health in the local neighboring communities. So it is very important that we analyze the economic impacts of the implementation of this regulation on the economy of the entire state. And more specifically, more importantly, we would like to evaluate what is the economic implications to the port-related sector as well as the transportation sector in general in California. All right, so a little bit more specifics of the case study that we are evaluating here. So we are analyzing the economic impacts of electrifying cargo handling equipment at Port of LA and Port of Long Beach And the study period extending from 2020 to 2045, 25 years of study period. And the major types of cargo handling equipment that are included in our analysis are, those that are shown here on this slide, including yacht tractors, RTG cranes, side picks, top handlers, and forklifts. So all of these major types of cargo handling equipment account for more than 95% of emissions at the port. And in this analysis, we mainly compare the changes of the cost of the equipment purchase of those equipment, and also the cost associated with any infrastructure upgrades or new construction of infrastructure facilities that are needed to accommodate the electrified terminals, as well as any changes in fuel and operation and maintenance expenditures relative to the baseline operation and regular turnover of conventional cargo handling equipment at the ports. And before we move on, I would also like to mention a few caveats here. So I would like to mention some key factors we have not included in current study, which of course are very important aspects that we expect to include in future research. So first of all, our analysis, the quantification of the costs of this electrification transition confined within the boundary of the port complex. So the first point here is about the port operations. So in our analysis, we does not assume any potential future transition to automation operation modes in additional terminals at the port. So in other words, we simply assume the port operations do not change except for the shift to all electric cargo handling equipment. And also, as I just mentioned, we just confined our quantification of the costs within the boundary of the port complex. And any potential costs associated with the upgrades and construction of the transmission facilities that ensure the supply of power to the port complex that need to be paid by the utility companies are not included in this analysis. So in other words, we simply assume there will be adequate amount of electricity resources available there to accommodate the electrification of the terminals at the port. And finally, the implications of this electrification process, especially in terms of the increase of peak load demand at the port, what is the implications to the port resilient operation is not the focus of this study. So in other words, any potential increased number of power outages or any impacts associated with disruptions of electricity supply, or the costs associated with some preparation and coping strategies, such as setting aside some backup generation systems, those costs and impacts are not included in the current study. All right, so next, let's take a look at the general analytical framework of this study. So this slide shows you a flow chart in terms of how we analyze the economic impacts, starting from the policy selection as well as the design of the policy in terms of the target year, the performance objective, and the sectors that are covered under this regulation, and the timeline of implication, and which sector will pay for the upfront cost of this transition, all of those elements of the policy design. And then based on those policy designs, we first quantify the So we first quantify the direct impacts of this transition in terms of the changes of equipment purchase costs, the costs associated with electrical and civil infrastructure related work, and also changes in fuel expenditures and O&M costs. And all of these are used as the inputs in our macroeconomic impact analysis model, the REMI model. I'm going to talk more details about how we make these linkages between the micro level and macro level modeling. And the output of the REMI model provide us both the impacts, the aggregate impacts on the state economy as a whole in terms of changes of gross state product, employment, and personal income, but also the impacts at the sectoral level. We are especially interested to know what is the implications to the economic activities in the port-related sectors. What is the implications to the market share and competitiveness of the transportation sector in general. So two main sets of results that are provided in our study. One is on the direct impact or the micro side, which include the upfront capital costs that are needed for equipment and infrastructure, changes in operation maintenance cost, and fuel cost savings. And on the other side is the macroeconomic impact, which is the results, the impacts on major economic indicators, as what I just mentioned. All right, so here are some more details in terms of the categories of direct cost and savings we quantified. So I will not repeat them again. Okay, so next, we actually made a lot of assumptions in our analysis. We have tried to use the best available, best data available at the time of our study, but it's also the case that there are many uncertainties associated with both the data as well as some of the design of the policies. So we try to make it apparent and clear and first list all the major assumptions that we adopted in the study, and this can also be used as the basis for our sensitivity analysis, so that we can change the values of those assumptions within reasonable ranges and see how that will affect our economic impact analysis results. So I will not go into details for each of them. So maybe I will just mention a couple of them. So for example, we assume a constant price level of the electric cargo handling equipment. So this is different from maybe you are aware of the price projections of the electric heavy duty trucks, because many studies project that there will be significant decline in the price in the future 10 to 20 years of the electric trucks. But it is not exactly the case for the cargo handling equipment. The primary reason is because it's, the cargo handling equipment, they are very specialized equipment. It has very small market. So it is very difficult for the manufacturers of those equipment to achieve economies of scale. So based on our discussion with the port experts, they suggest that for now, we just assume a constant price for those equipment throughout the entire study period. And also I'd like to mention, because we're looking at 25 years of study horizon. So depending on the useful life of those equipment, many of those equipment will have multiple replacement cycles over this 25 years. So there's this question, what is the replacement ratio between the electric equipment and their conventional counterpart? So this is a very important question because this highly depends on the battery capacity, the battery range. And again, based on our discussion with the experts, they told us that based on the minimum performance requirement demonstration and test at the ports, the requirement of 16 hours straight operation without recharging, that goal has not been achieved of those electric technology just yet. So what we did is that in our analysis, we assume an entire second fleet of cargo handling equipment, the electric CHE would be needed to replace their diesel-powered equipment counterparts. So just as I mentioned here, in the first replacement cycle, we assume a 2-to-1 replacement ratio. And then we also assume that battery technology development in the future can extend the range of the battery. And hopefully in near future, about around 2030 and after, it can enable a 1-to-1 replacement ratio between electric and diesel fueled cargo handling equipment. And there are also some other key assumptions, like the battery cannot last as long as the piece of equipment itself. So basically, we assume there will be one battery replacement required in the middle of the useful life of the equipment. And basically, the battery will cost about 2/3 of the equipment cost. And we also assume that the operation of the electric equipment would be the same as operating, a diesel fueled equipment. However, the maintenance cost will be lower by about 25 to 30%. And in terms of the energy costs, the electricity cost, we take into consideration the demand charge. So the demand charge is usually applied to commercial and industrial sectors because they have much higher peak demand of electricity compared to residential sectors. So this is a very important factor that would affect the cost of electricity for those electrified cargo handling equipment. And finally, in terms of which sector will shoulder the high cost, large amount of upfront capital investment cost of this transition. So based on the current available state incentive programs, we make, in the base case, we make the assumption that 10% of the total cost can be covered by the subsidies provided by the state incentive programs. And the rest, 90% of the cost, will be shouldered by the port sector. And the REMI model assume that the increased capital and production costs of the port will automatically passed on to the downstream customers through higher prices of the services provided by the port. All right, so a couple of additional notes here. All the results that I'm going to show next represent the incremental, the changes in cost and savings. And all of the results that are measured in dollar terms are in 2018 real dollars. And the results are presented in terms of both the simple sum of the cost, annual cost over the 25 years, as well as the net present values of the total costs using a 3% discount rate. And here are the 4 major types of economic indicators that we use to measure the impacts, the macroeconomic impacts of the regulation. All right, so first, this table shows you the total incremental costs. So positive numbers are incremental costs, and there's only one set of negative numbers here, which represents cost savings. So over the 25 years of study period, we estimated that the total simple sum of the total cost of electrifying all cargo handling equipment at the port will be about $8.9 billion. If we calculate it in net present value, is about $6.9 billion. And the equipment and battery costs account for more than 70% of the total cost. And the cost of charger and other infrastructure that are needed to accommodate this transition account for another 20 to 25% of the cost. So you see that the Yeah.
So those are billions then, right? Not millions?
those are actually millions. Yeah,
I'm noticing that the header says millions, but your thing
Oh,
to the
here.
side says billions.
yeah, because it's 6,000, it's
Oh, fair
6,000
point.
million. Yeah.
My obvious mistake. Okay.
Yeah, that's totally.
Yeah.
Okay. So, yeah.
Yeah.
So the upshot is it's in
No,
billions.
that was me.
Yeah,
Thank you.
billions of dollars of incremental costs here we are looking at. So if we look at the fuel cost savings, so maybe you would expect, the transition to electrified calculating equipment will result in quite significant fuel cost savings to the ports. But the results just to show, quite a small amount of that. This is primarily because of the high demand charge of electricity. Usually, right now, the rate is about 60 to 80% of the total cost of electricity. So you're going to see some sensitivity analysis on that in terms of, the extent that the demand charge dominates the electricity cost, how that will affect the total impact. All right, so this figure shows you more like a distribution of those costs. I just showed in the previous slides over time in 5 years intervals. So basically in earlier years, in earlier phase, the equipment and battery replacement costs accounts for a large share, as well as the infrastructure costs. So the primary reasons, first, because we are assuming a 2-to-1 replacement ratio of the equipment. So in the first replacement cycle, basically the first 10 years, a large amount of upfront capital investment in those electric equipment is needed. And at the same time, it is required by support Clean Air Action Plan, all the needed infrastructure to accommodate the electrification need to be completed by 2030. So that's another reason why you see a large concentration of, or large need requirement of capital investment in earlier stage of the transition. And in later years, battery replacement costs accounts for a larger share of the total costs because again, battery replacement is required several years after the initial purchase of those equipment. All right, so before we look at the macroeconomic impacts results, very quickly, an introduction of the REMI model. REMI stands for Regional Economic Models Incorporated, and we use the Policy Insight Plus PI Plus REMI PI Plus model. The REMI model has evolved over 30 years of development and refinement. So it is one of the most widely used macroeconomic impact modeling tools in the US, and many state government agencies in California, such as CARB, such as Department of Finance, and in Southern California, SCAG, and also South Coast Air Quality Management District, and many other agencies. They are using REMI model to analyze, proposed regulations or local development projects and programs. What are the economic impacts of those policies and regulations? So let me see. So the version of the REMI model that we use in this study divide the whole country into 2 regions. One is California, and the other is rest of the country. So that enables us to look at the relative changes of economic activities, between California and rest of the country, so that we can see whether there are some, potential shifts of economic activities because of the implementation of this regulation. And the model divides the whole economy into 160 sectors. So it provides very detailed disaggregated sectors like manufacturing sectors, transportation, energy production and supply sectors, and also commercial and services sectors, all of those sectors that depends on the services of the port. So I will not go into details. This is basically the structure of the REMI model. It's constructed based on 5 major model blocks, and all of those rectangular just shows the major variables within each model blocks and their linkages to variables in other blocks. All right, so this is the way that we do policy simulations in REMI. So starts from the formulation of the policy question, and then we identify the relevant external economic and policy variables that can, can be used to enter the inputs or external shocks to the model. And then the model is run without any shocks. So construct the baseline or control forecast. And next, we feed into the results of the micro level analysis results in terms of direct costs and savings. Those results that I just showed you as inputs in the REMI model, and the model runs generate the alternative or policy forecast. And then the comparison of the control forecast and the policy forecast delta here gives us the impacts of the policy. Again, I will not go into details here. It's just shows you how we link the micro level, the first column, the micro level analysis results to the REMI inputs. So the major thing we need to accomplish here is to identify the appropriate policy or economic variables in the REMI model, and also identify the relevant amount of 160 economic sectors provided in REMI, which is the appropriate sector to represent the final demand changes, or which sector shoulder the costs, which sector will see increased capital and production costs, so on and so forth, and then accomplish this linkages from the micro level analysis to the inputs of the REMI model. Okay, so next let's take a look at the macroeconomic impact analysis results here. So this table shows the total impacts in terms of employment, GSP, gross output, which is equivalent to business sale revenues, as well as changes in personal income. So we see that there are net losses of both employment and economic output primarily due to the high cost requirement of this transition. So the total employment impacts are estimated to be over 96,000 job years. So one job year represents a full-time worker working for 1 year. Okay, so this is the way we add up the employment impacts over 25 years in our study period. And the GSP impacts is estimated to be over $7 billion. All right, so here are the results, the average annual results in 5-year intervals, 5-year periods over the study period. And in this table, we present both in the first petition, we present the differences compared to the baseline economic projections, the baseline levels. And in the second part, you can see the percentage changes. So first of all, the impacts vary over time, and we see a greater, larger losses in earlier periods, once again, because of the high cost of upfront capital investment that are required, both from the purchase of equipment as well as the upgrade and construction of the infrastructures and facilities. And also another point here is that even we see some of the those impacts in absolute levels are quite significant. However, if we translate or convert them to percentage changes from baseline, all the impacts are quite small. No impacts is greater than 1/20 of 1% here. This primarily because of the large size of the state economy, which generated over $3 trillion of GSP and employed over 18 million workers in 2019. So that's why it is important we also look at the impacts at on the sector level. Before we look at the sector level impacts, very quickly, this is let me see. Okay, so this is the figure that shows you a decomposition analysis we did. So except for the aggregate impacts, we just look at what is the losses, job losses, or negative impacts on GSP and output. So what is the relative contribution of those individual factors to the bottom line economic impact results? So here those different color bars shows you the employment impacts in terms of, for example, increased capital cost of the ports, or increased demands of construction workers, increased investment in the equipment, so on and so forth. So this helps us to identify the major factors that results in both negative and positive impacts of this policy. So based on this figure, you can see the factor that results in the largest negative impacts is the increased capital cost of the port, the big burden of the cost, incremental costs that is going to be shouldered, or Georgia will be shouldered by the port, assumed in the base case. And some of the positive impacts comes from the increased investment, increased purchases of goods and services from the machinery manufacturing sector and also the construction sector, as well as the increased demand of electricity from the utility providers. All right, so one more thing, this bold black line here represent the net impacts. So you can see, those variations actually represents the high and low investment years over time, which is a combined effects of the replacement cycles of the equipment and batteries of different types of CHE. All right. Okay, so here are some sectoral level results in terms of the top sectors that are negatively impacted by the policy on this slide, and the next slide are those sectors that are expected to be stimulated by the policy. So the top impacted, negatively impacted sectors, not surprisingly, include port-related sector. This is how it is defined in the REMI sector. So it's under the support activities for transportation REMI sector. And it's also include the negatively impacted sectors, also include wholesale and retail trade, other transportation sector, and other services sector, etc. And positively impacted sector include the machinery, the equipment manufacturing sectors, the utility sector, the electric power generation supply sectors, and some electrical equipment manufacturing sector as well. Okay, so the next slides, we want to take a closer look at what are the impacts on the port sector as well as the aggregate transportation sector. So in this table, we present here the, the net present value of gross output changes. So it's, again, it's equivalent to changes in sale revenues of the sector. So in this table, we try to compare the output changes both in California and in rest of the US. So we see that gross output in both the port-related sector and the aggregate transportation sector in California decreases because of this regulation. At the same time, the gross output of those sectors increase in rest of the US. So basically this shows a potential shift or interregional substitution of economic activities or related businesses between California and the rest of the US. Again, you know, if we translate this $2.65 billion of a decrease in gross output into percentage term with respect to the whole state economy, the percentage impacts would be very small. But we can also, you know, look at this from the perspective of the port. So for example, the expected operational revenue of the two ports this year is about $1 billion. So if we assume a stream of this level of operating revenues over 25 years, the net present value will be around $16–18 billion. So in that case, the $2.6 billion would account for about 10 to 15% of the total operating revenues of the ports over the study period. So from this perspective, you can see the high cost required by this electrification transition is somewhat substantial from the port perspective. So that's lead to the next slides. So it's very important for us to look at what is the implications if we change our assumptions in terms of who pays this electrification transition. So once again, in the base case, we assume that all kinds of state incentive programs can help to subsidize 10% of the equipment and infrastructure costs. And the rest of the cost will be borne by the port sector and then passed on to the downstream customers. And here we run a set of sensitivity analysis on those assumptions in terms of the availability of state subsidy incentive programs, as well as the cost pass-through assumption. So the first sensitivity analysis we run, we assume there's no state incentive funding at all. So we just to try to compare the results of this sensitivity case with the base case to see what is the implications of providing government subsidy. And then in the second and the third sensitivity analysis, the cases, we assume that the 10% government subsidies in the base case has to come from somewhere. You know, there will be some offsetting effects. So in sensitivity case 2, we assume that this 10% government subsidy will be offset by reductions in other types of general government spending. And then in the third case, we assume that those money will come from increased taxation, increased government revenues from gasoline or other types of transportation fuel tax. All right. And finally, in sensitivity case 4, we assume that the port cannot pass you know, the 100% of the increased costs to the downstream customers, to the businesses directly and indirectly depend on the port services. So basically, we simply assume the port can only partially pass 50% of the increased costs onto the downstream customers. All right, so here are the results of those sensitivity analysis. So first, if we compare sensitivity case 1 and the base case, remember the first sensitive case, we assume there's zero state subsidies. So we can see the employment impacts, just to focus on the first numerical column. The negative employment impacts increased by about 9–10%. And even, you know, looking at sensitivity case 2 and 3, even we assume there's some offsetting effects, right? The subsidies provided by the state government has to be offset by a reduction in spending in other areas, or, you know, has to come from increased taxes on gasoline and other type of fuels. The negative impacts compare with the no incentive sensitive case, you see the employment impact, negative impacts is still lower. So that means it's very important to try to establish those incentive programs to help improve the economic performance of this transition. All right. And the last point here, if we compare the impacts of this partial cost pass-through sensitivity case with the base case, you see a lower negative impacts here. And the primary reason is that here we assume the port cannot pass the entire increased costs onto the downstream customers. So in other words, the large portion of the negative impacts will be absorbed by this single port sector. So that will reduce the negative supply chain or the multiplier effects to all the successive rounds of downstream customer sectors. So from the economic, the entire economic perspective, this results in a lower negative impact on the economy. But you can imagine in this sensitive case, the negative impacts on the port sector will substantially increase. Right. So this is just a shift of the distribution, the changes in the distribution of the negative, the cost burden of this electrification transition. We also did some additional sensitivity analysis in terms of the costs of the equipment and infrastructure, so on and so forth. So this based on our discussions with the experts of those equipments and the port operations, as well as our search in the literature. So here we formulated lists of assumptions that formulate the lower bound cost case, as well as the upper bound cost case. So this set of assumptions here are quite straightforward, but here for the replacement ratios, for the lower bound case, we assume it can be achieved 1-to-1 replacement ratio can be achieved earlier in around 2025, but in the upper bound, it's in the more pessimistic case, we assume it can only be achieved after 2035. And here for the cost of electricity, basically in the lower bound case, we assume a lower a percentage of demand charge. And in the upper bound cost case, we assume a higher percentage of demand charge. All right, so here are the results for both the base case for a comparison purpose here, presented here again, as well as the results for the lower bound cost case and upper bound cost case. So with the the reasonable range of potential changes in the costs, the total incremental costs of transition to electric CHE will range between about $5 billion to close to $9 billion. Okay. And in terms of the macroeconomic impacts, the employment impacts will range between about 6,000-7,000 job year losses to over 130,000 job year losses between the lower bound and upper bound cost cases. All right, so finally, let's conclude today's presentation by just highlights again some of the major findings in this study. So first of all, I just mentioned our estimation of the total incremental costs of electrifying the cargo handling equipment at Port of Erie and Port of Long Beach between 2020 and 2045 are estimated between 5 to a little bit more than $9 billion in that present value. And the majority of the costs will be the upfront capital costs that are needed to purchase the equipment, electric equipment, as well as the costs associated with battery replacement. And also the greatest incremental costs will incur in earlier stages of this transition process. And in terms of the macroeconomic impacts, we estimate employment losses between around 70 to 130,000 job year losses in the 25 years. And if we translate those impacts into percentage terms, they would be very small compared to the overall size of the state economy. But those impacts can be, somewhat substantial from the port perspective. And other sectors, except for the port sector, other sectors that will be negatively impacted include the general transportation sector, the freight transportation sector, wholesale and retail trade sector, etc. And let me see. Oh, based on the decomposition analysis, the increased capital cost of the port sector is the dominant factor that results in the large negative impacts on the state economy. And finally, based on our analysis of the relative output changes for the port and transportation sectors in both California and the rest of the country, we can see a potential shift of port-related businesses from California to other regions, other states. Okay, the various sensitivity analysis help us to identify some key factors that affect the bottom line, both the incremental cost of CGT as well as the bottom line macroeconomic impacts of this transition. Some key factors we identified, including the trajectory and the speed of the development of the battery technology when it can enable a one-to-one replacement ratio of the equipment, as well as the availability of government subsidy and incentive programs, as well as the extent to which the demand charge dominate the electricity cost. And the second bullet point here is that, again, we just confine our analysis on the port complex. We didn't consider what can be the implications of this, high increase in a very concentrated local place of high electricity demand. What is the implications to the whole power grid? And whether the power supply by Southern California Edison and RADWP can really accommodate this increased the peak demand load at the ports. So future studies are needed to evaluate those implications. And the very last point I want to make here is that we need to remember the primary goal of the zero emission transition of cargo handling equipment is to reduce criteria and also greenhouse gas emissions, and also to help to enhance the public health in the neighborhood, in the local community at the port. So a comprehensive evaluation of the impacts of this policy need to integrate the economic impact results you see here today with the environmental benefit, public health benefits of this regulation, as well as other potential co-benefits of this policy, such as the potential increase of productivity of port operation, through this transition, as well as reduced the enhanced energy security of the state by reducing the reliance on fossil fuel energy. All right, so that's all I would like to say. Next, so we can open to questions and discussions.
Yeah, anyone have questions? I have one on Zoom from Miwa Matsuo. She says, I guess your findings are more meaningful if you compare these net losses with gains in competitive advantages in the freight transportation market. I wonder how much more competitive advantage Long Beach Port will get by the investments.
Well, I mean, if we just based on the analysis we see here, it's actually, we see negative impacts, it's losses in terms of jobs and also output, because the port has to spend on the high investment, upfront capital investment cost to purchase those equipment to make the upgrade to the infrastructure, so on and so forth. But once again, I would like to emphasize that this study does not take into consideration the potential increased operation with the productivity that can be resulted from this transition in operation mode. But it's more complex because it can be, connected with the process of automation of the port and enhance the operation, also the capacity of the port. That can also, all of those can help to improve the operation capacity of the port and potentially increase the capacity, the competitiveness of the port.
Dan, can you hear me?
Yes.
Very good. I wanted to just add a little bit to the answer there.
Oh, yeah, sure.
And that is that we're working with it. We're working in a world where California is the only state imposing these regulations. So for the rest of the country, these costs are the same costs are not experienced. And so that's part of the answer as to why competitiveness and why the losses happen and why some business is lost to other states.
Yeah, so I totally agree. So we're just looking at the implementation of this regulation in California. So relatively speaking, we're just looking at the increased capital and production cost at the port in California in order to achieve those climate change mitigation goals. Yeah.
We have one more question from Nick Suarez. He says, if the horizon year of study period was extended, would you expect to ever see any positive gains in employment? From the earlier slide you showed with the jagged trend line, it looked like it was trending in that direction.
Yeah, once again, it's also depends on the future development of the technologies. And whether, so first of all, when we transition from a 2-to-1 replacement capability to 1-to-1, we can see a substantial decrease in the cost. And also the infrastructure, when it is upgraded and constructed there, this is just a more like a one-time investment. They can serve for quite a longer time than that. And also, although in this study we did not assume any decline of the prices of those equipment itself, if we're looking at a longer horizon, it's very possible the cost associated with those technologies and manufacturing of those equipment can decline in the long range. So we might see a more positive outcome from this.
Thank you.
I have a question here.
Oh, we have one question here.
Yeah, this is more of a kind of what you personally think. Do you think other states would eventually also implement any environmental mitigation regulations, or is it in the horizon now? It's only California. And from your
Yeah. So the question is that whether, of course, California is always the leader in terms of climate change policies and also the deployment of clean and renewable energies. But there are also many other states are leading the way. So especially some of the states that have a big ports like New York, New Jersey, they also implementing climate change action plans. So well, I would say that in the long run, we would see more and more state taking a more serious consideration, because the emissions from cargo handling equipment, as well as other sources of marine related activities, like the ocean going vessels and also the heavy duty trucks using the port, all of those are contributing large share of emissions. So I would think for those other states that operating big ports and they are very serious considering different types of climate actions to help to achieve greenhouse gas mitigating goals, they will eventually look into this potential.